when we prepared the work I'm going to talk about, I came already across the BayesiaLab website and the product, and judging from the tutorials and videos available, it looks really to be a really comprehensive and flexible framework. So I'm really looking forward to learning more about it. Okay, without any further ado, let's start. So I'm going to talk about Bayesian networks and nuclear data evaluation, but in order to appreciate, I think, what is going to follow, it is necessary to give you a brief introduction to nuclear physics for the purposes of this presentation. After that, I will talk about nuclear data evaluation, what it means, and finally, how we can use Bayesian networks to accelerate, improve the nuclear data evaluation process. So in nuclear physics, let's start with atom. And an atom is composed of a core and a shell. And the core, which is also called the nucleus, consists of neutrons and protons. And the core is enveloped by a cloud of electrons. In nuclear physics, we are only interested in the physics and the structure of the nucleus, of the core, and don't care about electronic shell around, which would be more chemistry. If we look at different elements and their cores, so they are distinguished the number of protons in the nucleus. Just to give you an example, if you look, for instance, at gold, it would have 79 protons. And if you look at uranium, it would have 92 proton elements. One element can appear in different varieties, which are distinguished from each other by the number of neutrons. And here, just as an example, here you see some gold. I guess this looks familiar. On the right, the bottom right, the picture on the bottom, uranium. And on the left, just as a picture, and in practice, is like a quantum physical system, so it's more complex than that. But for the sake of this presentation, you can think of the nucleus as a system of a number of neutrons and protons. And you can think the neutrons here are the blue balls, and the protons are the red balls or spheres. In order to learn more about the properties, the structure of a nucleus, one performs collision experiments. So one takes a beam of particles, neutrons or protons, for instance, focuses them on some target material, and then look at the different processes that are going to occur with what probability. And as an example, on the bottom right, a picture of a facility at CERN that sketches such an experiment. So on the right, you see a circular structure, a proton synchrotron, which accelerates protons, which are then led through some pipe where they travel to some lead targets, and there they collide. The protons collide with the lead nuclides, and produce in the process a lot of neutrons. And these neutrons are then used as a beam, and as a beam that is then focused on some target material where one is interested to learn more about the properties. The first concept, and a very important concept, is that you can see it as a property of the nucleus, is the total cross-section. The total cross-section is, you can think of it as an interaction area around the nucleus through which an incident particle has to go in order that an interaction between the nucleus and the particle is going to occur. And conversely, if the incident particle is too far away, so if the minimal distance of approach is too large, no interaction will occur, and the particle just passes by. And this concept of this interaction area is called the total cross-section. So it's really an area. And it's an additional complexity in this regard is that this interaction area is not constant, but it is a function of velocity of incident particles. And if we look at such an interaction area, a total cross-section, here in this case for gold, and as a function of incident energy, and in nuclear physics, people like to use more incident energy than velocity, but the concepts are related. So the larger the incident energy, the larger the incident velocity of the particles. Sorry, I messed up with my citation. So if one looks at the behavior of the total cross-section as a function of velocity, one sees that there are regions where it is quite smooth and well behaved for smaller velocities. But then once the incident particles reach a certain velocity, one enters the resonance range. In the resonance range, you see wildly fluctuating shape as a function of velocity. And only if the particles are still faster than corresponding to this range, things get a bit calm again, and you have again a smooth structure of the cross section. Typical, maybe you're curious about the typical distances we speak in nuclear physics. So the measurement unit to state cross sections is barn, and one barn is 10 to the power of minus 28 centimeters, which is about the same in square inch, because if you just look at the order of magnitude, it doesn't really matter if you talk about square inch or square centimeters. Sorry, this should be square centimeters, by the way. Okay, here to give you a bit of a clear picture how these resonances look like, I have here a zoom, and that it's really hard to model that you have spiky structures, and unfortunately up to this day there's no predictive theory in nuclear physics to predict the locations of these peaks and the amplitude. And this is important for nuclear data evaluation later. Once we have defined the total cross section, there are many. So once we know that something happens, so there is some kind of interaction between the nucleus and the incident particle, we are interested in to learn more about nucleus, what processes can happen. And here there are many processes possible. Here just 3 examples to give you an idea. The first process that can happen is that the incident particle hits the nucleus and then is deflected into some direction without transferring energy to the nucleus. This is called the elastic, and the probability or the cross-section which is related to this is called the elastic cross-section. The second process is that the incident particle hits the nucleus and is absorbed. And so the initial target nucleus is converted to some other isotope of the same element if you have neutrons. And the third example here is if that's the neutron hits the nucleus, is absorbed for a short time, and then two neutrons are emitted from the nucleus again. And you can think of, if you think of the interaction, the total cross-section as an interaction area where particles have to go through, you can think of these individual processes as taking one piece of this cake. So each of these processes has a likelihood to occur and they compete against each other. And so in a sense, a cross-section is nothing else but some kind of probability that indicates the likelihood of a process to occur. So I showed you 3 cross sections, but there are many more. And here is just an example, and they're related to each other according to the definitions. For instance, I talked already about the elastic cross section, where the incident particle is just deflected. Another cross section type is the non-elastic cross section, and there all processes are summarized where the incident particle loses some energy to the nucleus or is absorbed in it. And depending on the application, different types of these cross sections are important. And as I already mentioned, a cross section is not constant. It's not of constant size, but depends on the incident velocity. So all of these cross-section types are actually functions of velocity or incident energy. And now you may ask, okay, so far so good. Now we know what the cross-section is, what the nucleus is, but why do we need to know these cross-sections? Why do we need the dependence on velocity of these cross-sections? The reason is that the knowledge of these collisions and their dependence on velocity are important in nuclear engineering applications and also fundamental research. Here's a list of, probably an incomplete list of application areas where cross sections are important. Just to name a few, if you have a nuclear reactor, you want to be sure that the reactor runs in a stable mode, which means you should ensure that at each point in time, the same number of neutrons is produced and absorbed to have some equilibrium. If you look in astrophysics, and there people are interested in how different elements are created and their abundance in the universe and on Earth. And there you need to have precise knowledge about cross sections to model the collision processes correctly that appear in the core of stars. And of course, last example that we mentioned here, nuclear medicine. If you have a approach, for instance, if you have to perform a hadron therapy where you focus a beam with protons or carbon nuclides on some cancer tissue, you want to be sure that the collisions between the incident beam and then happen exactly in the cancer tissue and not in the surrounding and damage healthy tissue there. The fundamental challenges in obtaining the knowledge of the cross-section is, as I've already mentioned, there's no predictive theory in nuclear physics to describe the resonances. Furthermore, experimental data are not comprehensive, and a nuclear experiment is a really very expensive endeavor and can only be performed in a couple of places on the Earth. So it's really hard to get a comprehensive set of all the cross-sections that may be necessary to understand processes in astrophysics, for instance, at a sufficient level. And of course, there are nuclear models and they work in some energy domains, but they are usually less accurate than experimental data. So when we have experimental data available, we would like to leverage the experimental data as well and not only rely on our model predictions. So these are the challenges we are facing in improving the knowledge about cross-sections. And the pragmatic solution to address these challenges is the field of nuclear data evaluation. Essentially, there we collect data from various nuclear experiments, then quantify the uncertainties, and there's one brief slide afterwards what this means. It means of these experiments. If it's possible or pertinent, we can also include knowledge from the predictions of nuclear models. And then after the collection of all these ingredients, experimental data and nuclear models, we perform a meta-analysis to obtain a comprehensive set of the values of energy-dependent cross-sections, as well as their uncertainties. The workhorse, traditionally and still, is the generalized least squares methods. And before I talk, so I have a couple of slides on the generalized least squares method. But before that, let me just give you a brief idea about uncertainty quantification of nuclear experiments. Here, just a sketch of a nuclear experiment. As already mentioned, if in a collision experiment, you have a beam, that beam hits some target material, then some processes happen, other particles are produced, and some of these particles are detected in a detector. And in this process, a lot of possible error contributions which may distort the results of an experiment. For instance, we may not know exactly the average speed of the particles in the incident beam, or you don't maybe know precisely the spread of the individual velocities of the particles around the average speed in the sample. So this needs to be manufactured, and depending on the manufacturing process, impurities can happen. So maybe the target material has different thicknesses. If you think of a foil, different thicknesses at different places, and this introduces potentially another distortion. And then we have the detector. Detectors are not perfect, so sometimes they miss particles, and sometimes they are for different reasons. It may be that the particle just goes through, or another possibility is that the particles arrive too fast in sequence, and then the detector does not detect them individually, but just detects one particle. And finally, we can have some background contributions, so we can have some kind of radioactive sources from particles coming from the environment or from space that are also to some extent detected in a detector and add additional noise to the measurements. So this by itself is a really ideally the experimentalists do a very comprehensive work on this and to have all the error contributions quantified. But it's a very time-consuming task, and challenging task to get all the uncertainty contributions correct. So after this brief slide about experimental uncertainty quantification, I want to start with the mathematical part, which is now we get to the Bayesian network, the application of Bayesian networks for the purpose of nuclear data evaluation. As I've already mentioned, the workhorse is the generalized least squares method. And in the Bayesian paradigm, here are the assumptions. So we have some quantities of interest, P, here in the first, you can see them in the first line. And we assume we have some prior knowledge about these quantities, which we quantify as estimates and standard deviations and correlations. So we construct a micro normal distribution. And then we have some probabilistic link of these quantities to experiments we can perform. And there again, we assume that the propagated parameters P can be compared with the experimental measurements, sigma x here, up to an uncertainty characterized by an experimental covariance matrix P. And then we can apply the Bayesian machinery. We can just multiply these two distributions together, which are called prime and likelihood. And we can combine them in the Bayesian update formula to obtain a posterior distribution. And in using the assumptions I've just mentioned, multiple normal distributions plus a linear link between the P and the experimental data, we obtain the posterior is another micro normal distribution, and we can calculate the center vector of it and the covariance matrix analytically. I will not talk more about, so this is the most mathematical slide in my presentation you can find. I will not talk more about this in detail. But the only thing I want to mention here is that in the Bayesian network stuff I'm showing on, we have worked on, we have relaxed the assumption of the linearity. So we're not dependent anymore that our models are linear and still can use this approach as a submodule in the inference procedure to get precise maximum a posteriori estimates for quantities of interest. Here, just briefly, so the general least squares method has a long history, at least 40 years, according to a report I found on our website. If you're interested, you can read it. And after that, let's get to the Bayesian networks. So I showed you all the cross sections. I showed you that they're related by, that they can be regarded as some kind of graph that connects them to each other according to the definitions. And I've also shown you a sketch about an experiment and talked about the potential error contributions that could be present. So if we forget now about the nuclear physics part and just look on it from an information theoretic perspective, we can equally say that we have some kind of modules, components, experiments with their certain equipment, and all of these things are connected to each other by certain links, mathematical links. And I think so. This naturally, I think this really cries for the application of Bayesian networks, looking on nuclear data evaluation from this perspective. And in the following, I'm going to show you the specific choices we have made in the construction of our Bayesian networks. The first, so the basic building block here, just two nodes with a link from X to Y, and this link, which is here just written F, it can be any nonlinear and I would say differential function, connects X, which is a vector in our case, to another vector Y. And it is important. So we're dealing with, I've shown you before, we are dealing with functions which are connected to each other. And in the approach, in the Bayesian network approach, as we use it, we discretize the function. So each function gets converted to a vector, The other thing which we need as a modeling assumption is what kind of distribution to use. And we are using, without exception, micro normal distributions. So this is the same assumption as for the generalized least squares method, but with the important addition that because of the fact that we allow nonlinear links between nodes, we are in practice able to deal with more with more distributions than just the micro normal distribution. And here I give you some examples how this works out in practice and what distributions you can deal with. For instance, if you want to model a quantity positive, as is the case for cross sections, we usually model it classically as a log normal distribution, and we can implement this in the Bayesian network by introducing a link between one node X and Y that forms the XY element-wise exponentiation of the elements in X. Another possible transformation, and this is very popular in machine learning with neural networks, is the rectified linear unit, where we just truncate our values that are negative and set them to 0. And there are a couple of more linear interpolations if energy measures don't perfectly overlap that we can use. The last ingredient in our tool set to construct Bayesian networks for nuclear data evaluation is, of course, the sums, as I've shown you with the cross sections. So if we have a sum of two nodes which are propagated nonlinear, we can also depict it as a block in a Bayesian network. And here's an example why we would use this practice. If we have an experimental measurement, which is y here, for instance, and we have a model prediction, convoluted model prediction, maybe given by the propagation of x, then we know that these quantities, the prediction will not perfectly match the experimental measurements due to the error contributions I mentioned before. And so finally, before coming to the end of my presentation, I want to show you how we really can apply Bayesian network modeling in practice. So as an example, I had to take neutron-induced cross-sections, so neutrons hitting on iron 56 between 1 and 2 MeV incident energy. This energy range is particularly suited for a demonstration because it only comprises a few cross-section types which are relevant, and these cross-section types are the total cross-section, the elastic and the inelastic cross-section. And according to the definitions, the total cross-section is given as the sum of the elastic cross-section and the inelastic cross-section, approximately as the sum. There are just some other channels, but they are negligible. And the colors here match the colors of the nodes, match the colors of the functions. So the green one, for instance, the green node corresponds to the green function. And again, we have wildly fluctuating functions in this energy range. And now we can do a bit more sophisticated modeling, because you see, yes, the functions are wildly fluctuating, but if you do look at the average trend, it seems to be quite smooth and doesn't change that much. So in order to account for this, we can extend the Bayesian network can do more fine-grained modeling by regarding each of these cross-sections as the sum of an average component, a function which captures the average, and another node which captures then the quickly fluctuating oscillations on top of the average. And then, because of the definitions, we need to conserve the constraints, like the sum of the average component of the elastic cross-section and the inelastic cross-section must equal the sum of the total average cross-section, and the same is true for the highly fluctuating component. Experimental data, it's straightforward to add them as nodes. Maybe we need some, as I mentioned before, some mathematical operations to make the prediction or the true cross-sections comparable to the experiments by broadening them, by smoothing them a bit. But in principle, this is straightforward. And finally, this I don't have time to speak about it, but in detail. But if we can only measure the sum of something, and then we have two nodes, it's a highly underdetermined system. So without any regularization or prior constraints, we will not be able to make reasonable inference. So for this reason, compared to the Bayesian network I've shown you before, for illustration, true network, for instance, we have developed for this case, contains a few more nodes which act as regularizing nodes. For instance, we take we pose some constraint on the second derivatives of these functions to have some smoothness, and we also enforce some integral constraints, that the integral of the highly fluctuating function over small intervals should be approximately 0 in order to be sure that the average component really node captures the average component. And finally, some results to show that it works as expected if you use reasonable assumptions. Here you see again the elastic estimate, maximum a posterior estimate of the elastic cross-section, the inelastic one and the total one, and as a comparison, also the binned averages of the experiment data, which are shown here as blue horizontal lines. And that for the inelastic and the total cross-section, the maximum a posterior, the map estimate, closely follows the binned averages, which is really nice. This is what we expect. But you also see that this is not the case for the elastic cross-section. And again, what I mentioned, you can usually not directly compare smooth behavior of a cross-section with the highly oscillating experiments. So therefore, let's also look at the other component, not the average one, but really what Bayesian network thinks is the true network, as the true cross-section. And here you see the picture looks a bit different. So we still have modeled the elastic and total one nicely, and also for the elastic one, suddenly we are below. So you see it's. So I think this shows that it works, but you also see that we should be really careful in the precise modeling of experiment data. So this brings me to my summary. I gave you a brief introduction to nuclear physics and made a case why the knowledge of cross sections is important for several applications such as astrophysics, nuclear medicine, nuclear energy. Unfortunately, that's not a comprehensive predictive theory to compute them. Therefore, we need to practice a combination of experiment data and models to estimate to obtain good estimates. And it seems like Bayesian networks are really powerful in modular framework to model all these intricate relationships between different cross-section types, experimental data, also to account for known constraints. Thank you for your attention.